to start our lecture on advanced reaction engineering. So, today we will discuss about multi-phase reactors. So, we have discussed there are various type of multi-phase reactors, that is slurry reactor, trickle bed reactors, fluidized bed reactors. So, here today we will discuss basically the slurry reactors. So, in the slurry reactors basics equations or design equations, particularly the modeling of the slurry reactors, that we will discuss, and gas rates of gas absorptions, transport of catalyst, diffusion and reactions, how they are related with the this particular reactor modeling, and rates law, that basically we will discuss. So, the modeling of slurry reactors. So, here you can see the slurry reactor that we are going to discuss. In these particular reactors, if we take any reactant, that is the gas, liquid also molecules, that is another reactant that we can use inside of a reactor. So, here you can see this is the schematic diagram of a slurry reactor. So, here in the left hand side you can see this is a slurry reactor. So, at the bottom of the reactor we are passing the gas. It is a basically component A plus B going to another component. Component A is the gas and B is the liquid, and if we take any solid material, that is the catalyst. So, here three components are there, one is the gas, liquid and solid. So, when these three components come in contact at a particular temperature, pressures, so then that product C formation should be there. Okay. So, in this type of particular slurry reactors, you can see at the bottom of the reactor gas is passing, here is sparger, through that it is gas bubble formations is there, that bubbles will be go up. Here this is the part of component where reactions will take place. Here liquid, from the beginnings we have placed liquid is there, and solid catalyst particles, that is remain there inside of the reactor. So, at the beginning inside of the reactor solid catalyst particles are there, and liquid, that is the second reactant, that is also remain inside of the reactors. So, if we maintain temperature, then reactions will not be take place, since there is component A is not available. So, when A is passing from the bottom of the reactors and come in contact here with the three components gas, liquids and solids, then these reactions will take place. Okay. So, these are the reaction when three different components are present, three different phases are there, therefore, it is called multi-phase reactor. So, there are few examples I will discuss about the hydrogenation reactions, particularly gas of hydrogens, and this is the second component methyl linoleate, that would be converted into methyl oleates, that is another liquid component. And similarly, hydrogens, that is reactant A, that would be used to unsaturated fatty acid to convert it into saturated fatty acid in presence of nickel catalyst. So, here reactant 1, reactant 2 and catalyst, that is the present inside of the reactor, and so we have to use this type of reactor. Then we can conduct the reactions and convert the reactant component B into another component. Similarly, other reactions is also there, hydrogen plus glucose or fructose in presence of nickel catalyst, we can convert into sorbitol, or acetylenes and formaldehydes we can convert in presence of copper acetylides, that is the catalyst, 2 propane 1 ol or propargyl alcohols that we can produced, or for this particular system acetylene is the gas and this is the liquids, and this another product, that formation is there. Similarly, another example is vegetable oil, that is the unsaturated oil in presence of hydrogens and catalyst, we can convert it into saturated fat, that is this type of reactor is useful to conduct this type of reactions when gas, solids and liquids are present in the system. So, when we are going to design or modeling this type of reactors, so before modeling, so we need some assumptions. These are the assumptions for modeling of slurry reactors. Number 1, liquid phase is well mixed. So, here inside of the reactors you can see gas, liquid and solids are there. Here we are considering liquid phase is well mixed with the catalyst and gas. Catalyst particles are uniformly distributed. So, here inside of the reactor gas, liquid and solids are there. Here catalyst, that is the solid particles, we are assuming that it is distributed uniformly, and the gas phase, that is gas component, that is here hydrogen, that is flowing inside of the reactors in the form of plug flow. Okay. So, these are the assumptions. Based on this type of reactors we will study, and we develop some model equations to solve this type of reactors, to find out means what would be the rate limiting steps, or how we can, what are the factors are there, catalyst weight, flow rates, stirring speed. So, many things are, catalyst particle diameter, so many things are there, how that would affect, or also here gas and liquid reactions is there. So, gas absorption is very important. So, how that we can improve, means increase the gas absorptions for a system. So, that we will discuss. Okay. So, in this type of reactions, I said it is a gas, liquid and solid phase reactions. The reactions in the slurry reactors we are taking, then these are the following steps are there, means when gas liquids come in contact with the solid surface. So, at the beginning, step 1, that is the absorptions of the gas phase into the liquid phase at bubble surface. When here that gas is entering inside of the reactor for the reactions, through these purges it would forms gas bubbles. Here is the gas bubble, you can see. So, through these purges, gas when pass inside of the reactor, it would form spherical bubbles. That bubble diameter also we can control with the help of spurger diameter. By changing smaller to higher range, we can increase, decrease, that way also bubble spherical diameters, bubble diameter also we can add, increase or decrease. So, here the absorptions of the gas into the liquid, first step is the absorptions, means when gas is entered inside of the reactor. So, gas will get absorbed with the liquids. Okay. And next step 2 is the diffusion in liquid phase from bubble surface to the bulk liquid. So, whence gases come to the in contact to the surface of the liquid, then that gas would be diffused, or that would be transferred from interface to the bulk liquid surface. And then third step is the diffusion from the bulk liquid to the external surface of the catalyst. I said there is the 3 parts are there, 3 components are the gas, liquid and solids. So, first liquid component and will come to the interface, then it come to the bulk liquid surface, and then bulk liquid surface to the catalyst surface. So, diffusion from bulk liquid to the external surface of the solid catalyst, external surface of the solid catalyst, there is the diffusions from the bulk surface to the catalyst surface. Then internal, step 4 is the internal diffusion of the reactants in the porous catalyst. So, then internal diffusions means when that reactant molecules come in to the surface, external surface of the catalyst, then it would diffuse, different pores are there inside of the catalyst. Since the catalyst is a porous component, active sites are there inside of the pores and the surfaces of the catalyst, that internal diffusions would be there, means the reactants will diffuse to the external surface to the internal surface of the catalyst. Then step 5 is the reactions. Reactions in the porous catalyst, when that reactant molecules A, B come into the porous catalyst inside of the pores where active sites are present, there it is reached, then reactions will take place at the step 5. So, these are the reaction steps, means gas, liquids that would be react in presence of a solid catalyst, how the reactants A, B come into the contacts with the surface of the catalyst in the pores of the catalyst for the reactions. So, these are the steps I said. So, absorptions of the gas, then diffusion of the gas into the liquid bulk phase, then diffusion from the that particular gaseous component from the bulk liquid to the external surface of the catalyst, then internal surface diffusions, means from the that reactants will diffused in the inside of the catalyst pores, and then surface reactions will take place. So, once reactants will enter, then product formations would be there by reactions, and then products would be diffused the reverse way, means from inside of the pores to external or outside surface of the catalyst, that will they will diffuse, that would follow the reverse directions. So, here when we want to discuss about these gas, liquid and solid phase reactions, then gas whatever we have taken, that is in the form of let us say bubbles. This is the gas bubble, gas is present component A or hydrogens whatever. So, that is in the form of gas bubbles. Here is the liquid. So, here is the liquid. So, gas, this is the interface, this is called interface, means gas and liquids, that is in between that part, that is called interface. Here's gas is there, a layer, another layer is the liquid. So, here's mass transfer would be there from the gas to the liquid surface. So, here's the how many in the liquids, how many moles or amount of concentrations of component is there in the liquid, that we can find out using, and for that we have to use Henry's law. So, Henry's law is C I equals to P I into H prime. So, here H prime is the Henry's constant. For hydrogen it is this value, it is coming, and P I is the partial pressure of component A. Here component I is the hydrogen, okay, or A you can say. So, component I concentration C A or C hydrogens, if you want to know partial pressure of hydrogen into Henry's constant. So, this way we can express. So, concentrations of hydrogen in liquids, if you want to measure, then partial pressure of hydrogens we know, means the pressures that is present for due to the hydrogen or gaseous component in the system. So, if you know the partial pressures, if you multiply with the Henry's gas constant or Henry's constant H prime with that partial pressures, let us say here we are supplying in this gas, let us say hydrogen pressure is equals to 10 bar. 10 bar pressures we are supplying the hydrogen in the systems in the reactor. So, then here we have to use 10 bar or 10 atm whatever, and then H primes we have to multiply. H prime, since here for hydrogens it is given mole hydrogen per atm per dmq, then we can convert this 10 bar into 10 atm, and then H prime we can multiply, then concentration of hydrogen in the gas phase, component gas in the liquids, that concentrations we can find out. So, this is the concentration of liquid. So, concentration of component hydrogen in liquids, that we can find out. So, concentration of liquid phase is related to the gas phase concentration is like this. Okay. So, here's this way we can find out or we can use these equations. So, if it is directly concentrations is given, then so we can find out, or if it we can use for our means numerical solutions. If it is given in terms of pressure, partial pressure of that particular component at which that gas component is passing through the reactor, that we can put it here. Okay. So, here the 5 steps we have discussed. So, here you can see it would be much more clear, means how actually in the systems how each component taking part in the reactions or diffusions reactions is going on. So, here this is a gas bubble I said, and this is liquid, and this is catalyst particle, that is the solid. So, gas, liquid and solid. So, 3 components are there, 3 phases are there. So, here gas in the form of gas bubbles, it has a particular partial pressure Pi. So, here this is the interface, this here this is the liquid, here this is I said this is liquid, this part is liquid and this part is gas. So, at this interface mass transfer would be there or absorption would be there, means gaseous component would get absorbed in at this particular point, that is the interface concentration that we can find by using Henry's law. So, once it is get absorbed at the interface, interface means gas liquid interface, then it would diffuse to the liquid. This is the liquid, in liquid bulk concentrations. Okay. So, in liquid that component gas that it get absorbed by diffusion or mass transfer, the concentrations would be bulk concentration of component A, that is the hydrogen. So, this is the bulk concentrations. After that, this is the I said solid catalyst, solid particles, that is in the form of sphericals we are considering. So, this is solid particles. So, here from the bulk of the liquid to the, this is the surface of the catalyst, external surface, this is the surface. Here gas molecules from the bulk liquid to the gas that would come. So, initially bulk concentration was Cb and surface concentration was Cs, let us say. So, then this is the driving force for the mass transfer. So, here component A, that is diffuse or travel by this resistance and it would reach to the surface of the catalyst. So, after that, once that reactant molecules A reach to the surface of the catalyst, this is the external surface concentrations, then it would diffuse inside, internal diffusion. Internal diffusion means it is diffused to the inside of the catalyst pores, I said before also. So, this is called catalyst pores. So, here catalyst active sites are there, reactant CAS is there, and then it would enter inside of the pores in the active sites of the catalyst, then it would take part in the reactions, and then internal diffusion should be there. This is called external diffusion and this is internal diffusions. When internal diffusion is when the diffusion or mass transfer of reactant molecules from external surface to the inside of the pores, it is diffusing, means transferring from one point to the inside of this catalyst particles for the reactions. Then once it is reached to the inside of the particles, here component A, then it would take part in the reactions and reactions will occur. Okay. So, here 4 and 5 steps are there, means internal diffusions reactions that would occur inside of the catalyst surface. So, these are the steps. So, each steps you can see there is some resistance is there 1, 2, 3, 4 and 5. 5 steps are there and 5 resistance are there. This is resistance 1 for absorption resistance, this is 2, number 2 is this internal interface to bulk, means the reactant molecules come into the surface of the liquids. This is gas, this is liquid if we say. So, liquid, this is the interface point. So, here gas molecules come in here and then it reach to the bulk. Okay. So, this is another resistance and third resistance is bulks to the catalyst surface. If catalyst surface is there, so there's that molecules will enter another resistance, resistance 3, and then internal diffusion or resistance, and at the same time reactions will take place there if we maintain that particular temperature is required for that reactions. So, then reactions will take place. So, now individual resistance we will find out, individual resistance for that rate equations we will derive, and based on that the design equations for this particular systems and what are the factors are there. So, how we can control to get an we can design a efficient slurry reactor. So, that will discuss basically here the step 1 gas absorptions I said, that is the from here that is come to the here means step 2 from the bulk interface to the bulk interface to the means for absorptions Henry's law is there. So, the interface concentrations we can find out, and then interface to the bulk the mass transfer will take place, and for that rate of absorptions of A RA, that is the rate of absorptions mole per dmq solution per unit second, it units. So, moles of that moles of A component that is transferring from point this point to this point. So, then the resistance or driving force, concentration driving force is Ci minus Cb, that is the driving force. Within that driving force the rate of transfer or mass transfer will take place. Then rate of absorptions for that particular steps we can write Ra equals to Kb into Ab into Ci minus Cb, where Cb is the bulk concentration of the hydrogen or that gaseous component in the solution, Ci is the gas component concentrations in the interface, gas and liquid interface concentration, and Cab is the Kb is the mass transfer coefficient, gas phase absorption coefficient, and Ab is the bubble surface area per unit volume of the solution. Okay. So, Ab is the bubble surface area dm square per dmq solutions, it has unit. So, individual components unit is concentration unit mole per dmq and bubble surface area dm square per dmq solutions, and mass transfer coefficient, that is the Kb, is it has unit dm per second. Okay. So, this is equation 1 for interface to the bulk, rate of mass transfer for component A, that or the gaseous component hydrogen. Next step is the step 2 transport bulk solution to the catalyst surface. So, from Cb this is the bulk concentration to the Cs. So, at this point to this points the resistance is there, rate of mass transfer that will develop equations. So, rate of mass transfer of hydrogen from the bulk solution to the external surface of the catalyst, that is we can express, that is R equals to Kc Ac m Cb minus Cs. Cb minus Cs, that is the driving force in between bulk concentration of the component hydrogen to the surface concentration, means catalyst surface. So, that is the difference. If there is concentration driving force or difference is there, only mass transfer will take place from one point to the another point. Therefore, this is the driving force. Rate of mass transfer also I said that has the same unit. Here you can see mole per DMQ solution per unit time. So, here also it has the units mole, that is component A transferring or changing per unit volume of the solution per unit time. So, here Kc, that is the mass transfer coefficient for particles, Ac is the external surface area of the particles, it has unit dm square per gram of the catalyst. So, whenever solid particles it has a surface area that we if you want to calculate or measure surface area usually per unit weight basis, meters dm square per gram of the catalyst, and this is m is the mass concentration of the catalyst, the gram catalyst per unit solutions DMQ solutions that was taken, that we can put it here. So, if we multiply all these right hand side, in the left hand side that would come as mole of component concentration DMQ solution per unit time, that would come here. Okay. So, this is the second equation from transfer of the component A or hydrogens from the bulk solution to the surface of the catalyst, external surface of the catalyst. So, this is the rate of transfer. Here you can see AC, that is the external surface of the particles, that we usually write area per unit mass. Area, if let us say r is the radius of that particle, spherical particle of the catalyst is has a r radius, or dp is the diameter, we can say dp is the diameter or r is the radius. So, here 4 pi r square, that is the area, and volume and density of the particles if we multiply, then that would be mass of the catalyst. So, after that if you simplify, it would give 6 by rho into dp. Okay. So, dp is the diameter of the particles, rho p is the density of the catalyst. If we know, then external surface area of the particles per unit mass basis, that we can calculate. Diameter of the particle is known and density of the particle is known, then external surface area of the particles per unit mass we can calculate. Okay. So, next is the diffusion and reactions inside of the catalyst particles. So, when the reactant molecules reach to the surface of the catalyst, then third step is the internal diffusion and reactions. Internal diffusions and reactions, in that case the rate we can express in terms of this minus R A prime equals to eta minus R A S prime. R A S prime minus R A S prime, what is this? At suppose that reactant molecule reach to the surface, external surface, and internal diffusion is there. If the surface concentration of that all the internal surface, if we consider it is exposed and there is no resistance, then the ideally the rate of the reactions will get, that is would be higher. So, that is the ideal rate actually. So, in actual rate we are getting this minus R A prime, that is the actual rate or real rate for spherical particle, there is a internal diffusions resistance are there, therefore, the actual rate we are getting this, but this is the ideal rate. Or if the inter-reactant molecules rate at the external surface concentrations, if the interior pellets were exposed to the reactant concentrations at the reactant surface or external surface concentration, Ca is the external surface concentration, let us say Cas, this is the Ca surface concentration, and inside of the reactants there is concentration is different. So, means here reactants, this is the inside of the pores, here concentration would be different, that we will discuss in our later class. So, how internal or external diffusions play roles. So, for a spherical particles, so that part we will discuss in later. So, now here is the surface concentrations, this is the, if see here inside the concentration is different, external concentration is higher. So, if we assume that instead of a spherical particles, active sites area inside active sites of that catalyst remain inside of that catalyst particles and inside of the pores. If it is exposed, then large number of surface active sites will be available, and in that case the rate would be overall higher. So, this is the rate we can write this way, that is the efficiency. Okay. So, it now the rate we can write RA, that is the mole per DMQ solution per unit times. This is, if we multiply it, this actual rate with mass of the catalyst, gram of the M with M is the gram of catalyst per DMQ solutions. Okay. So, if let us say 1 liter of solutions or liquid solutions we have there, if we use 1 gram of the catalyst, so 1 by thousands, that way we have to write the concentrations or mass of the catalyst that have been used for that particular reactions. So, here if we actual reactions rate, if we multiply it, here reactions rate, see here in terms of primes. So, moles of the catalyst, moles per gram of the catalyst per unit second. So, here the rate we are converting into per DMQ of solution per unit volume basis. Here per unit mass of the catalyst was this rate was in terms of mole per gram catalyst. Here prime is there minus RA prime, that is per unit mass of the catalyst, and RA here per unit volume of the catalyst. Okay. So, moles A react per DMQ solution per unit times rate of reactions. Okay. So, if we multiply minus RA prime with M, then if we substitute minus RA primes here, so then rate of for these reactions we can, for internal diffusion and reactions, the rate we can write this equals to M eta minus RAS prime. So, here's M unit of M is this and minus RA prime unit is this. If you multiply that, then it would be this. Eta has a dimensionless, it is the ratio of the rate. So, that is you can say minus RA prime by minus RA prime AS. This is the rate. Okay. So, it is the ratio rate. So, your maximum value may be once for a particular system or maybe more than that, that we will not discuss later. So, consider here eta value, that is the efficiency. Okay. So, now this equation 3 for diffusion and reactions we have derived, this is, and now rate law. Okay. So, considers here the reaction is gas and liquid phase. So, when liquid and gas reactions both are the reactants and solid is the catalyst. So, here's rate we can write minus RA prime equals to K prime, that is the constant, Cl0 that is the concentration of the liquid, initial concentration, and C is the concentration another component, or that is here we can say it is the component of B, hydrogen. Okay. C, that is we are considering hydrogens, and Cl0 that is the liquid. So, this way we can write the rate equations. Here the concentration of the liquid we are assuming Cl equals to C naught or Cl0 that is the constant, Cl0 that is the constant, means virtually means when we have taken large quantity of the liquids and we are passing reactant molecules, that is the gaseous component A, through that in the form of bubbles. So, we are assuming that the concentration of the liquid virtually remain constant. So, therefore, K prime Cl0 that we are considering small k, specific reactions rate. Okay. So, that we are considering, and then minus RA prime equals to small k into C, here C is the concentration, external surface concentrations. Okay. So, then this equation 5 we can write. Okay. So, minus RAS prime equals to, if C equals to Cs. Okay. So, then we can write minus RAS prime equals to K into Cs. So, these equations is useful that we can substitute in these equations. Okay. So, equation 3 we can substitute equation 6, equation 6 minus RAS prime, that is the rate of the reactions or disappearance of reactant component A at external surface concentrations. The rate equations we can write rate of reactions at the external pallet surface minus RAS prime equals to K into Cs. These equations we can substitute in this equation 3. Okay. So, then once we substitute that equations, okay, that lectures I am doing. So, then overall transport rate of transport at steady state, we can say that when all the resistance are there and then the reactant is passing from gas to the internal surface of the catalyst by travelling so many resistance. So, then rate at steady state all the rates would be the same. So, then this is for interface to the bulk, that is the changes rate of transfer of the mass or for component A or component hydrogens from bulk to the surface, this is the rate, and for internal diffusion and reactions, for that this is the rate. So, equation 6, if you substitute this in equation 3, then equation 3 is there and equation 2 is there and equation 1 is there. So, these 3 equations are there. So, now this at steady state, if we consider that rate equals to this equals to this equals to this, means all the rates are equal at steady state. Okay. So, then we can here we are substituting. So, see here minus in the case of equation 3 is minus RAS primes, we are substituting from equation 6, and after substituting it is coming m eta k c s. Okay. So, now these equations and this we have. So, these 3 components are theirs at steady state. So, now these 3 components with RA we can write this way. Okay. Just this component we are expressing this way. Okay. So, RA by this KB and AB we are putting here and Ci minus Cb that we are putting in the right hand side. Similarly, for component this and this we are writing this way, Cb minus Cs we are keeping right hand side and left hand side we are dividing Ra with Kc, Ma and Ac, we are getting this. Similarly, Am eta K Cs is theirs, we are putting Cs in the right hand side, Am eta K that we are dividing Ra with this. So, then it is coming this. Okay. So, then these 3 components means at steady state the rate we are writing this way. Okay. So, now if we sum up all this left hand side and right hand side, then you see that Cs, this Cs will be eliminated if we sum up, Cb and this Cb would be eliminated if we sum up. Okay. So, then see here it would be clear. So, here adding all these 3 components and then we are taking Ra outside of the brackets and inside it would be this, and Ci would Ci is left in the right hand side, that is why we are writing this. After that we are rearranging these equations, Ci by Ra, if we divide Ci with Ra then it would be this. Okay. And right hand side is this, left hand side that is the Ci by Ra and right hand side all these components. Okay. Or simplify you can write 1 by Kb AB, that is Rb we can writing, and these are the parts here m small m is there, we are taking out from the brackets and rest of the terms is there. So, here these terms we are writing as Rb and rest of the terms 1 upon Kc Ac that is equals to Rc and 1 upon eta k that is we are writing as Rr. Okay. So, then this equation is coming. So, here Rb is the resistance of the gas phase absorptions, this part absorptions resistance, and this part is external mass transfer resistance, that is due to the external transfer from bulk liquid to the surface, and this is reaction internal mass transfer and as well as reactions in the surface of the catalyst. So, here these resistance and these 2 resistance are there. So, after that if we again simplify these 2 resistance we are combining into RCR, that is the combined resistance, external diffusion resistance as well as internal diffusions plus reactions. So, here it is 2 resistance are there, external diffusion resistance, internal diffusion resistance plus reactions resistance. So, this is the equations, final equations we have developed. So, here we can write these equations, here Rb and Rcr or 1 by m Rcr, that is very important. So, if we for this reactions, for any reactions, if we know let us say these are the components are known and 1 by m, m is the mass of the catalyst per volume of the solutions that was used for that particular reactions. So, if we plot C I by R A against 1 by m, then the graph and plot it would be like this. Okay. So, here C I by R A against 1 by m we are plotting. So, it would be start, the lines would be like this. Here this part is the intercept and this part is the slope. Okay. Slope equals to this R C R, that is the slope. If we plot C I by R A against 1 by m, so intercept would be R B and slope would be R C R, that is equals to R C plus R R. Okay. So, graphically we can express this, that finals equations here this way you can, this is the gas absorption resistance. Okay. So, at this particular point, see here if we go linearly, means at this way along the x axis, this part is constant, means gas absorption RB basically indicate gas absorption resistance, and this part actually the slope indicate this resistance, internal and external and reactions due to the reactions inside of the catalyst pellet, that resistance. Okay. So, that way we can measure, means how much percentage of resistance is there for this particular gas liquid solid reactions, the due to the gas absorptions how much percentage resistance is there. So, from this intercept we can find out whether it is gas absorption resistance is there or not, and at the same times from the slope also we can find out the resistance due to the diffusion, external as well as internals. Okay. So, rest of the part we will discuss more details in our next class. Okay. So, here if we this intercept, let us say intercept actually indicate the gas phase absorptions and this is diffusional resistance. Okay. So, if we change catalyst particles, either increase or decrease amount of the catalyst for that particular reactions, see the gas phase absorptions that would not affect, that remain the constant, only changes would be that diffusional resistance part that will affect, this part linearly will absorb, but this part would not affect if we change catalyst quantity more or less, since the gas phase absorptions that is related with the gas and liquid, not with solid particles. So, gas phase absorptions resistance that depends on in between that, not catalyst. So, how much catalyst we are placing inside of the reactor, that does not affect, but after that the if we change the 1 by m, that is the amount of the catalyst, either it is increasing or decreasing. So, then that would affect the overall diffusional resistance. Okay. So, this is the absorptions and this is the diffusion. So, this part if you write this way, intercept and slope. So, it actually indicate the two resistance, okay, absorption resistance and diffusional resistance. Okay. That way you can write. So, intercept by slope multiplied with m. So, this way also we can write. Okay. So, two different resistance we are considering, absorptions and diffusional resistance, and rest of the part detail about that, how we can change one resistance, means absorption resistance we can control, diffusion resistance we can control. So, we can increase the conversions rate or rate of the reactions for that particular system, that we will discuss in our next class. Okay. Thank you. So, today is up to this. So, we will discuss more details in our next class. Okay. Thank you.